Good morning, everybody. Today we talk about caches. I understand that you are familiar with the idea, that you know what caches are basically for, and that you also know that caches may occur in multiple levels. Those levels are largely transparent in the sense that a higher level cache will see the lower level cache the same way it sees memory. So a lower level cache provides the same view to a higher level cache as memory does, except that the access is faster. So when discussing the functionality and organization of a cache, it will do if we focus on a single level. So we'll focus on the level that is closest to the CPU, because this is the most interesting level from our point of view. A cache consists of a number of blocks, which we call lines, to tell them apart from the memory blocks that can be stored in those lines. The size of a line, its capacity for data, is always a power of 2. The typical size of a cache line may be 64 bytes. It doesn't absolutely always have to be 64 bytes, but this is the sort of ballpark figure. In this little example of ours, we assume that the size of a cache line is 8 bytes. It would be considered a bit on the low side for a practical cache, but well, perhaps not. It will do for the illustration. The number of lines in a cache is also a power of 2. So all the numbers are powers of 2, and they are also nice and round. A cache line may contain a block of data from memory. So assuming that the size of a cache line is 8 bytes, again, sort of imagine that the first 8 bytes of memory amount to block number 0, the next 8 bytes from memory amount to block number 1, and so on. Given a memory address, the address of a specific byte in memory, the number of the block to which this byte belongs can be obtained by dividing the address by the size of the cache line, which is 8 in our case. You know that to divide a binary number by 8, you have to shift it to the right by 3-bit positions. This is because 2 to the power 3 is 8. So, well, generally, dividing by powers of 2 is easy. So, for example, here we have a block starting at address EC78 in hexadecimal. This is the first byte of the block. We know that this is the first byte of the block because this address is divisible by 8. So we say that this address occurs at a block boundary, or put differently, that this sequence of bytes starting at A is aligned at a block boundary. How do we know that this address is divisible by 8? Because the 3 rightmost bits of the binary representation of this number are 0. So given an address, we can transform it into the block number by simply shifting the address some number of positions to the right, and this number depends on the size of a cache line. Now, the idea is called locality. Okay, so the whole concept, the whole usefulness of caches stems from the phenomenon of locality, which means that given a program, it usually does not need all its data or all its code continuously in a sort of uniform sort of way. Once a program gets to doing something, it's going to spend some time doing some specific things and referencing some specific data and running some specific code, perhaps a sequence of functions and so on. So its activities will be localized in memory for a while. This implies that we can perhaps improve the performance of this program, meaning increase its execution speed, if we organize the memory in such a way that some portions of memory will be held in some quick, fast, perhaps small storage, representing the parts of the data and the code that the program needs at the moment. Okay? And we can implement this storage using some advanced technology and make it fast, because it doesn't have to be big. It doesn't have to be big, because statistically the activities of programs tend to be localized. We will return to this phenomenon, or we'll discuss this phenomenon from a slightly different angle, but only a slightly different angle, when we get back to paging. Because paging, especially virtual memory, which is the next topic in our course, is also based on the phenomenon of locality. Okay, for now let us focus on our cache, and let us think of ways of implementing it. Okay? So a cache line is supposed to store a block of memory, and we know how to transform a memory address into the number of memory block. Okay? Now, how would we implement this kind of storage? So we would probably organize those lines into some kind of an array, and then here on the left we have indexes in this array. So this is line number 0, line number 1, and so on. Then we would of course provide room for the data. So this is the buffer to accommodate a data block. And then we would need some way to identify which block is present in which line. So we can assume that there is a field which we call the tag, and this field contains the number of the block that is present in the cache at the moment. We may need a special value in this tag field to indicate that the line does not contain a valid block of data at all. And the need for such a special value will become clear in a while. Okay? So now, when the CPU issues a memory address because it wants to access some data or some piece of its code, this address is fed into the cache, and the cache is supposed to tell whether the referenced block is in the cache or not. Okay? Simultaneously, the same address is sent to the next level cache or to the memory controller. So this is done in parallel, such that if we fail at some stage, the stage that works slower is given a chance to accomplish something while we are waiting for the response from the higher level. Yeah? So it all works in parallel, and whoever is first to respond, well, responds. So if the reference block is present in the cache, then the cache is supposed to respond. So the cache must be able to identify the block, to tell whether the block containing the reference location is present in the cache, and if it is the case, respond with the contents of the block. So I can imagine that the cache scans its lines for the value of tag that matches the block being referenced with the memory access, right? And we know how to transform the address that is issued by the CPU into a block number. We just do something like this, okay? So like in this particular case, line number 1 is tagged with 1D8F, which happens to be the block number of this location, right? So in particular, if the CPU references this byte, wants to get hold of this byte, it will issue this address. This address will be transformed into the block number. The block number occurs as one of the tags at one of those lines. So the line will respond, okay, I have a copy of this block. If the mechanism fails, then the memory block will be accessed using the slower mechanism, be it the next level cache of memory itself, right? And while this happens, the line will be, well, one of the lines in the cache will be filled by a copy of that block. And the line will be marked appropriately such that next time around, the cache will be able to locate the block within one of its lines. Okay. Now, so I said, okay, so the cache scans its lines for the right value of the tag. We can imagine that in an actual implementation, this scan must be fast, because otherwise, well, cache would be slower than memory, right? So there must be some techniques to make sure that we don't just go one by one through all those lines, comparing some value to some other value and sort of looking it up sequentially. There must be some hardware that parallelizes this search. And this hardware, we can imagine that this hardware is expensive because its complexity depends on the number of lines. There might be some wires that go through all the bits of those tag fields, and there is some way to make one of those lines, the right one that contains the right value, respond somehow, send the data, and so on. This is not an architecture course, and we don't have to, and we shouldn't go into technical details, but you can imagine that there is some complexity involved, right? So it is a complex hardware mechanism. But this is what we call full associativity. Full associativity is the property of the cache that it can actually search in parallel through all the values of the tags to identify one line that holds the referenced block. So this mechanism is complex because of this parallel search, where all the lines are scanned at the same time for a specific value of the tag. And one can think of simpler mechanisms of associating cache lines with addresses or memory blocks, block numbers. For example, we can assume that there is a simple transformation of the block number into the index of the cache line. Now, if the number of cache lines is a power of 2, then, for example, we can think of something like this. We take the address, we transform it into the block number, same way, and then we just look at some number of bits within the block number. Like if for example, the number of lines is 256, which is a nice power of 2, then if we cut the rightmost byte of the block number, this will give us directly an index into one of the cache lines. For example, assuming that we want to reference this block, with the block number being 1D8F, when we apply this operation, we'll obtain 8F, which is the rightmost byte of this value, from this value, okay, which is 143 in decimal. So this address and this block number will be transformed into a single specific cache line, line number 143. So we can assume that this particular block, if needed by the program, is always going to be stored into one specific cache line, line number 143. So this gives us a very simple mechanism of transforming an address into the corresponding block number. There's just one simple operation involved, but we lose quite a bit of flexibility because now we are forced to store every given block into one particular cache line. So we have easy access, so the cache can be faster, but the cache is less flexible. Why is it less flexible? Because now it constrains which lines are used to accommodate which blocks. So the program has less flexibility in making sure that the cache contains the actual bits and pieces that the program is needing at the time. Because if, for example, the program wants to use this block and yet another block whose number seems to fall into the same cache line, then the cache will be able to accommodate only one of the two blocks. In the previous case, in the case where we had full association and we could store any block into any line, we could accommodate both blocks. We could accommodate any blocks as long as there was enough room for them, enough lines in the cache. Here we have collisions and we have to decide which of the blocks we care more about. Okay? So we have this trade-off. We can have a very flexible cache, which is difficult to build, costly and expensive and cannot be too big. And we have a simple cache, a simple mechanism. This looks like a straightforward array. When we know how to implement it, no big deal. Can be large, can be inexpensive, but its performance is likely to be worse. Okay. Let us note that in this direct mapping, with this direct mapping approach, we still need the tag field, because when we transform the block number into the index of a cache line, we still have to make sure that the cache line actually contains the right block. We can reduce the size of the tag because the fact that we have ended up at this line tells us quite a bit about the block. Like, for example, in this case, we know what the least significant 8 bits of the block number are. Okay? So we don't have to store this part in the tag. So we can reduce the size of the tag by removing from it the part that is transformed into the line index. Okay? So the two extremes, full associativity and direct mapping. The cache is characterized by its size primarily, which is the product of the number of lines and the line size. Both numbers are always powers of 2, which means that the product is also a power of 2. Then there are the associativity rules. Cache can be fully associative, where any memory block can be accommodated into any cache line, or direct mapped on the other end of the spectrum, the least flexible of them all, where a given memory block can only be accommodated into a single specific line determined by some simple function of the block's number. Quite often we have something in between, because a fully associative cache cannot be too large. You can have a large direct mapped cache, but its performance is not going to be terrific. So there is a way to trade between the two, and I will say a few words about it shortly. Then there is the replacement policy, how the cache lines are recycled. When the CPU, the program, references some data in memory, and the block containing the data is not present in the cache, then it has to be fetched and put into one of the lines. The question is which line it is going to be put into. If we have a direct mapped cache, then there is no flexibility at all. We know, given a memory block, we know in which line we have to put it. And then we just put it there. The previous contents of the line are evicted, as we say. If we have an associative cache with any degree of associativity at all, then there is a choice. In particular, if we have fully associative cache, then we can choose any line at all. And if we have a choice, any choice at all, it makes sense to choose wisely. And we choose wisely when we select the line that contains something that is not going to be referenced for a long time. By the very definition of what the cache is for, The cache is to store things, stuff that is needed by the program, that is recent, that is relevant. So if you have something that is not going to be needed for a long while, then it is irrelevant, can be evicted, and the line can be recycled to accommodate something recent, something relevant, something like the block being referenced. Okay. Then there is the write policy. What happens when the program writes something to a data block that is present in the cache? Okay. Memory references can be for reading and for writing. When we write something to the cache copy of some data block, we have to worry about bringing the memory copy of the block up to date. We will see why, but it is pretty obvious. There may be multiple processors, multiple CPUs running threads of some distributed applications, and they worry about a consistent perception of memory, right? So we have seen those issues in the context of synchronization. Okay, so there are situations when multiple processes and multiple processors in particular worry about their consistent perception of a block of data. Now, if different CPUs have their private caches, they may have different perceptions of the same data, and they worry about bringing those perceptions in sync. So here we have it. Suppose that we have multiple CPUs, and we actually care about these caches, the closest caches to the CPU, and each CPU has its private cache. Okay, if there is a lower level cache in between, then it doesn't cause any problems as long as it occurs as a single mechanism, global mechanism, right? So the role of this cache is to present the same view as physical memory to these local caches, except that it is faster. But there is a single mechanism for this cache, which means that the perception of physical memory is always coherent and always consistent. It doesn't cause problems. But those private caches, they do bring in potential for problems. Well, we can imagine that we have those CPUs run multiple threads of, say, of a distributed application, and those threads want to communicate, want to synchronize by accessing a shared data structure. So at some point, one of those threads so here is the data structure. I'll try to do some drawing. It's not going to look nice, probably. So one of those threads fetches a portion of this data structure, a block, to its local cache and operates on it. And then it may happen that the other thread does the same. So now the same data structure, or at least portions of it, have different views from these two different CPUs. Okay, and everything is fine for as long as the programs, as the threads, only read the data structure, access it for reading. The structure doesn't change, so these perceptions are consistent, are the same. But when one CPU writes something, modifies the data structure, then we have a problem. The problem is, okay, what to do with the other copy? First of all, we should recognize somehow that another cache holds a copy of this data structure, and the copy is no longer up to date, and we have to do something about it. We have to enforce its modification. Okay, and that's what the problem is about. So about the simplest solution would be to force all writes to always go all the way to physical memory. But this still doesn't solve the problem. This is actually how it is done in some cheap old caches. Okay, so caches are fine for reading, but when there is a write, then the write operation goes all the way to memory just to make sure that the authoritative copy of the data structure, which by definition resides in memory, is always up to date after every write. Well, this kills the performance of the cache for writing, but still, well, there is some improved performance for reading, and you can argue that reading is more frequent than writing, so there is some improvement, but it will not do for contemporary systems, which are obsessed about performance. Okay? So, well, but this clearly will not do. Even if we update the memory copy of the data structure, we still have to make sure that the cached copy on the other CPU is also updated, right? So we need some kind of a kick to this other cache to do something about its obsolete copy. For example, this kick may amount to invalidating the entry, the line holding the second copy. Contemporary caches on multi-core systems implement sophisticated mechanisms of bringing themselves up to date. So, in particular, when one CPU writes something to a cache block, there is a mechanism that checks against other copies of the same block in other caches and makes sure that at most after a while, those copies will be brought up to date. Okay? But we should be aware of the problems. We should be aware of the fact that this cannot really work miraculously and instantaneously, because if it did, then it would kill the whole idea of caches. So the cache consistency coherence problem is a big problem. There exists sophisticated mechanisms that try to solve it, but it cannot be perfect, in the sense that there is always some delays, there is always some issues. Well, we don't really want to go too much into details. I just want to familiarize you with one buzzword, snooping, which is a sort of generic name for the sophisticated techniques employed to maintain the coherence of multiple caches in a multi-core systems. So the general mechanism consists in monitoring the operations, the data transfers that go between the CPU and the caches, and especially monitoring the addresses, because they identify what is going on. Okay, so for example, when one CPU writes something to a specific block, the address of this block is involved. And then there's a mechanism for intercepting those addresses and comparing them with the addresses of blocks stored in the other caches and triggering events. Okay? And there are whole algorithms, coherence algorithms, expressed in terms of reacting to those events. Okay? Another category of events is the events triggered by the transactions between the caches and the memory, or the next level cache, which is the same thing. Okay? So, for example, when one CPU fetches a block of data, this block of data is put into the CPU's private cache, it may happen that the cache would like to know that it is holding the only copy of the block among the other caches. Because if it knows that, it knows that it doesn't have to worry about the coherence of the multiple copies in the other caches. So it is an important item of knowledge. Now, when another CPU is fetching the same block of data, this will trigger an event at this level, at the level of snooper, and then the status of the blocks will change. They will be marked, for example, as shared, meaning beware that there is a copy of the same block in another cache, which means that on some occasions I have to worry about issuing some special events there, such that those other caches can bring themselves in sync with my copy. Okay, so there is some buzzwords and there is some sophisticated mechanisms, a whole class of problems that are rightfully discussed in a quite advanced course on machine architecture. So these issues are complicated at the hardware level, and they are mostly transparent. So all this sophisticated hardware tries to hide the details such that casual programmers or even professional programmers of regular applications don't have to be aware of them. Okay? But every once in a while, a professional programmer, a programmer who deserves this title, stumbles upon some issues that are related to those problems, and then some knowledge can go a long way. Okay, so what do we have to know as professional programmers about those issues? First, local caches create multiple views of potentially the same memory area. Those views are synchronized. They need to be synchronized, and they are synchronized on contemporary systems. The problem is that the automatic synchronization is not always perfect, it's not always immediate, and we have to remember, we have to keep this at the back of our heads. Okay? Now, this is only the tip of the iceberg, actually, when it comes to the problems that may result from various tricks that contemporary systems play to improve their performance. So we have those optimizing compilers that are free to rearrange code to speed up the execution of your program. And they can play tricks with the code. They can permute instructions, for example, because they only worry, if not told otherwise, about the sequential semantics of the program. It means about how the program is going to work when viewed as a single sequential thread. The optimizing compilers are free to do this because when they are free to do this, they can reorganize the code in a way that optimizes its execution time, that minimizes its execution time. This isn't directly related to caches, but may cause similar problems. The problem is that you look at the program, you see some sequence of instructions, everything is fine. The program executes correctly as a single thread. But now when this program coexists with other threads that make assumptions about the order in which the instructions are executed, then we stumble into problems. Then the contemporary hardware is also allowed to optimize. For example, the CPU can execute instructions out of order if it sees that they are not dependent. They can come up with its favorite way of executing those instructions, favorite order of executing these instructions, such that the total amount of time needed to execute them is minimized, as long as the CPU thinks that it doesn't disturb the sequential semantics of the sequence of instructions. Then the memory controllers are even allowed to permute memory references, the order of memory references, and the order of fulfilling them, as long as they think that the sequential semantics of the sequence of references is okay. So now for some illustration. So here is the old algorithm by Peterson for two-process synchronization. Okay? We discussed it a while ago, and I'm not going to repeat its discussion. Just recall that the idea, the essence of the algorithm, its correctness hinges on a certain property. This property being that when process 1 arrives at this stage and is trying to check the condition, P2 trying and cookie equals 2, it assumes that if the other process wants to enter the critical section, it has executed these two operations. And when it comes to its copy of the condition, it will see P1 trying equals true, okay, set to true. Okay? So, in other words, process 1 wants to know that by the time it is looking at P2 trying, the fact that P1 trying has been set to true, and perhaps the fact that cookie has been set to true, these facts have been communicated to anybody who may be doing the same condition on the other control variable, right? Now, so what is the problem? Well, the problem is that first, when the compiler looks at this code, it may think like this. Okay, here we have this assignment, and here we have this other assignment, right? But let's have a closer look. Is there any place between these two assignments when the value of P1 trying is used? Let's have a careful look. Where can it be? Nah. So why bother? Let's just skip this assignment and set only P1 trying to false at this point. Then, if the compiler has even a closer look, then it may see, okay, nobody really cares about P1 trying in this code, right? So who cares? Let's just discard it. Okay, the program isn't going to change its sequential semantics. When viewed locally, there's nothing that P1 trying is used for, right? So there's one thing that an optimizing compiler may do to your code, right? And then there's the second thing. Supposing that you have somehow managed to force the fact that P1 trying exists at all, and that those assignments are carried out. Now, when you look at this code, there is nothing that makes it mandatory for this operation to be actually carried out before the first check for P2 trying is made in the loop, right? When you look at the code, this operation occurs first, this operation occurs second, but these operations are not dependent really, right? The outcome of this operation does not seem to depend on whether P1 trying is true or false. So the CPU or the memory controller, any of the sophisticated piece of hardware that is in charge of running your program may decide to postpone this operation. Postpone this operation arbitrarily far into the future, say after the first check for P2 trying, which will mess things up, right? And then, of course, on top of this, we have the cache coherence problems. You said P1 trying equals true. You are writing something to a memory location, like you are holding to your own cached copy of that memory location. The question is, when is the other copy used by another process who may be looking at the same chunk of memory, when is it going to be updated? And the answer is, I don't know. We don't know. This is why when you program these processes on a contemporary system, on a contemporary multi-core system, try to run them, you will see that they don't work. They don't work in the worst possible sense. Namely, both processes are allowed to enter the critical section at the same time. So much for Peterson's algorithm. Okay, so is there a way out? Well, the contemporary architectures know that they can mess things up, but they also provide means to resolve the issue if memory consistency is needed, okay, at the moment when it is needed. So there is usually a machine instruction. Sometimes there are several instructions with slightly different parameters and slightly different flavors enforcing slightly different things. I represent them. I represent the relevant hardware requisites with this barrier operation. Okay, this isn't any operation you can automatically find in your favorite programming environment. Just represents the tools that you have to look up on the system on which you are doing your work. But they basically amount to this. At some point, you put some instruction on some operation, and following this point, all the memory writes that have been issued before this operation have been actually issued. So the operation guarantees that when you proceed past the operation, then any outstanding references to memory have been carried out, and everybody then that can possibly care about the contents of that memory has the correct perception of everything. Okay? Well, so now with this operation we resolve the problem. We only make sure that before we start looking at the control variable of the other process, we have enforced the view of whatever we have done so far at the other process. This is going to do the trick. Now, mind you, when you are using the tools provided by the operating system for synchronization, like semaphores in pthreads or anything, then those tools are guaranteed to work by the virtue of them being system calls, which means you run a process, now you ask the operating system for some synchronization. Okay? Now, when you cross the boundary separating your process from the kernel land, the system takes care of everything. First of all, there is a context switch, and a context switch means one thing. Everything that the process has been doing is nicely and neatly saved as the process context. The process doesn't have to worry anymore about any outstanding memory references that may go out of sequence. Okay? This is guaranteed by the fact that when the system takes over, it has to preserve the context of the interrupted process. So don't worry about this when you are a standard programmer. It always uses tools provided by the system. But every once in a while, in advanced programming, in advanced multi-threaded programming, we want to do something by hand. We want to do some simple synchronization using spin locks, for example, or tricks like that. And then we may get into a situation where we have to enforce the consistent perception of memory at some other parties. And here's another little problem, perhaps less critical, because nothing will go wrong if you don't care about it and you don't solve it, but the program may experience a performance loss. This performance loss may not be big, usually people don't care, but if you are a perfectionist, then sometimes you should care, or at least you should be aware of the problem and of the possible ways of solving it. So what is the problem? Well, we know that whatever gets fetched into a cache line is a memory block that is aligned at an address that is divisible by the size of the block, right? Now, if you have a data structure, and this data structure is assigned some place in memory, then it may happen, like, okay, let me try to do some drawing, that the structure crosses the boundary of two or maybe more blocks. So we can imagine that we have two blocks in memory, okay, two consecutive blocks in memory. These are the blocks that would go into cache lines when the data structures in them are referenced. And you have a data structure that falls at some address in memory, and the data structure crosses the boundary of these two blocks. Okay, so this is where this data structure, the bytes of this data structure actually fall. So now what do you have? You have a data structure whose parts occur in two different blocks. Now when you want to reference the structure, like for example, it may be an array of bytes for simplicity. Right? When you want to reference this structure, you will have to make sure, well, the CPU will have to make sure, the hardware will have to make sure that both blocks are in the cache, right? So now, what is the problem? Well, first of all, when you are scanning through this data structure, when you are referencing it, two blocks will have to be brought into the cache, which is more than one block, right? Definitely is going to cost more in terms of time, right? So when the second problem is that if you are using two blocks to represent a data structure that could fall into one block, then the other block, one block is wasted, one cache line is wasted, okay, because you need two to accommodate the data structure. Perhaps it would make sense to use that underline for something different and still relevant to the program. It would be better. The contents of the cache would be better attuned to the program's needs, right? So sometimes, of course, you don't have to worry too much about this. After all those automatics in the cache mechanisms is at least partially to relieve the programmer from worries of this kind. But if you are obsessed about the performance of your program, then you may want to align the data structure such that it falls entirely into one cache line. and if you know the size of the cache line, you can, there are arcane and obfuscated tools to do this. For example, what we see here is a way in GNU-C, to force the alignment of a data structure at a specific boundary. So if you know, for example, that the length of the cache line is 16 bytes, you can force the alignment of this array to an address divisible by 16. And this will guarantee that the array will fall into, well, this one will not actually fall into a single cache line because the size of this array is 8. So assuming that the size of an integer is 4, it takes 32 bytes. But at least it will be aligned nicely at 2 cache lines. Okay, we can fix this example, and we can change this to say 32, and now it makes, oh yeah, now it makes better sense, right? Alternatively, we can replace this 8 by 4, and then it still makes sense because the total size of this array, assuming a 4-byte integer, is 16 bytes, which matches the size of the cache line. But anyway, it doesn't really make not very important. But one of those little tricks that you can apply to improve the performance of your program. Well, of course, this only makes sense if there is a really critical data structure that's accessed all the time and you have a number crunching programs whose execution takes hours, right? But sometimes you have a problem like this. And here's another problem where cache alignment may be useful. Okay, imagine that you have 3 variables that are used by different threads of your multi-threaded applications. Those threads are likely to be run on different CPUs because you have a multi-core system, right? When you declare 3 variables like this, they will go into adjacent locations in memory. So assuming there are 4 bytes each, they will go into a chunk of 12 bytes located at some random place, right? Quite likely they will fall into one cache line. And then there is a problem. You have 3 threads, each of them uses a different variable, and that all 3 variables fall into the same cache line. And we have the old coherence problem. When thread 1 writes something to its variable, the coherence mechanism of the cache will try to enforce the coherent state of the line, and the line also covers the variables used by the other threads. So in all 3 threads, this block will keep flashing among those caches. There will be some sophisticated operations going on to try to bring the line in sync, even though those threads use actually different variables, and they may not care for the status of the other variables, right? So we have false sharing, means that those threads don't really want to share those variables, but they accidentally share them anyway because the variables fall into the same cache line. Okay, so in a situation like this, you would worry about putting each of these 3 variables into a separate cache line. And here we have another little issue, or maybe non-issue, depending on which way you want to look at it. Remember test and set? This operation in a single atomic step reads the value of a variable and sets it to some known value like 1. The operation must be atomic with respect to any other threads that may be executing at the same time and looking at the value of the variable at the same time, which means that its implementation must necessarily circumvent all caches, affect the value, the authoritative copy of the value in memory, and then make sure that while the operation is being carried out in its entirety, no other process can use the old value of can use the value of the variable, even if it has it in its own cache. So this is a complicated and expensive time-wise operation that must hold the current process until the operation gets all the way through, and along the way it must account for all the cached copies of the value of the variable, all the possible cached copy of the variable at other processes. It takes time and it takes effort. It's a costly operation. Now, why would you speed it up? Well, this is a spin lock. When you want to use test and set for a spin lock, well, you would normally go like this. But then it is spinning, and on every turn of this loop, it carries out this extremely expensive operation that does just exactly what I said. Okay? Here is a better way to implement a spin lock on a system on which you worry about the efficiency of this operation. Okay? How do we do it? Well, we execute test and set, but if we fail, then we don't just keep spinning, we enter a while loop and we check the straightforward value of the flag using a straightforward check, straightforward read for 0. Okay, what is the idea? Well, we don't want to try another test and set until we learn that the value of the flag has changed. To learn that the value of the flag has changed, we don't need to do any hardcore mechanism that holds everybody still until we are done. We can simply check the value of the variable in a sort of straightforward way, but by looking at our cached copy of the value. For as long as the contents of the variable don't change, our cached copy will keep returning non-zero. When it becomes 0, there will be some cache coherence mechanism that will eventually bring our copy up to date. So we'll see, oh, now flag has changed. But now in order to grab it properly, we have to re-execute test and set. Okay? So we are not guaranteed that we will succeed, but we stand a good chance. So only try when we stand a good chance of succeeding, as opposed to spinning with this heavy operation, blocking the interface, blocking the memory bus, and blocking the caches of everybody. Okay? So one of those tricks that professional programmers do when they implement spin locks. And in order to understand what this trick is about, you have to understand what caches is about and what the problems of cache coherency is about. And just a bit more on caching. Well, I told you that, well, there are those two extremes when it comes to a cache's flexibility, fully associative and direct mapped. And I also told you that quite often we see something in between. So how do we implement that in between part? Okay? So the idea is quite straightforward. The idea is to grab a bunch of fully associative caches and put them together into a kind of second level direct mapped cache. Okay? So the idea, it would go like this. Suppose that the line size is some power of 2. Okay? Like, we know that it tells us that we should ignore some number of least significant bits of the address. The remaining portion of the address will be used as the block number. Okay? Because everything is aligned to the line size. So the first thing about that you want to get is the block number. Okay, so we ignore some number of bits from the right. Okay, fine. Now we take the next m bits from the right and use those bits as an index to identify one of those associative caches. Okay, of course the number of those caches is also a power of 2. So it is easy. The number of those caches is 2 to the power m. So we just take m bits from the block number, and this will give us directly the index of one of those caches. And within those caches, we use the fully associative mechanism to identify a specific line. Okay? So we have partitioned the whole large cache into blocks, into super blocks, each super block being a fully associative cache. Okay, and then we say that a cache implemented like this is a k-way cache if any given memory location can be cached in any of k-specific lines. Okay, what does it mean? Well, here we have the flexibility. So any particular memory location, like when we look at any particular memory location, it gives us a particular block number. We look at the block number, and the rightmost m bits of this block number tell us which super block we are supposed to use, which associative cache we are supposed to use. So we are not flexible here. But once we get there, we have k ways to accommodate the block, right? So we don't have all the ways, we have just k ways, where k is much smaller than the total number of, maybe much smaller than the total number of cache lines. Okay, so this is how we trade between the two extremes.